Howdy, stranger. Welcome to part 3 of this series. In the previous parts, we got the game to a mostly playable state, but there's one crucial part of what made this game so good in the first place which we haven't touched yet, and that's audio. We'll tackle that next, and we'll even add some small improvements along the way, so we have quite a lot to talk about. Grab your headphones and let's get started. We could of course just use SDL to implement the game's audio, but it's somewhat limited in its capabilities, so instead let's use OpenAL. More specifically, we'll use the OpenAL soft library, which is a nice cross-platform fork from the original, which was Windows only. We'll use it to play all the game's sound effects, and since no one uses CD audio anymore, we'll replace the music with some OGG Vorbis files, so we'll have to write a player for that. First we have to grab the OpenAL soft library from GitHub, so we'll just get the latest release there. Next we'll go ahead and also grab the latest version of the Vorbis library, also from GitHub, which will contain the decompression algorithm for our music files, and finally we'll also need the OGG library to go with it, as that contains the audio file container code. Now we can proceed to unpack all three libraries, and we'll start by setting up OpenAL. It's made up of three parts: a DLL file, the library code for our linker, as well as the include headers. We'll copy the libraries into our third-party libx86 folder, then we'll copy the headers by copying the entire AL folder into our third-party includes, and finally we'll copy the softoal.dll file into our runtime folder, but we'll have to rename it to openal32.dll. That covers it for OpenAL. Now on to the OGG Vorbis pair. We'll deal with OGG first, so if we go to the Win32 folder, we'll find a nice Visual Studio solution ready to go. Upon opening it, we get a pop-up from Visual Studio asking us to update the Windows SDK and Platform Toolset versions in the project. Just hit OK and it should work out of the box. Now we can simply change the build type from debug to release and the target to 32 bits, as that's what we're currently working on. Hitting the build solution button creates the libogg.lib file which we want. We'll rename the libogg 1.3.6 folder to just libogg, and we'll need to move it to the same directory which contains the Vorbis library. We'll be compiling the static version, so let's open the corresponding Visual Studio solution. If we try to compile now, it will fail, as it won't find the OGG library, so before we do that we need to edit the libogg.props file. We just need to put the correct version number for the OGG library there, and now we can compile. The README file from the Vorbis library explains these steps. Now we can copy all the library files and their includes into our third-party folder. We'll start off by adding the audio libraries into our linker inputs list, and while we're there we should now be able to remove the directsound.lib, directdraw.lib, and dxguid.lib entries, which we added in the first episode to get the game to compile. Now we'll set up a header called OpenAL Audio, where we can already define three necessary functions which will initialize, clean up, and update our audio system. Following that, we'll create the corresponding CPP file and start implementing these three functions. First off, we'll include the required headers and set up some constants. Next up, we add some arrays which will hold our audio buffers and sources, and we'll already add variables to hold our music buffer and source. Lastly, there's a variable called global ball, which is used in the original direct sound code, so we'll also use that. Next, we can write our initialization code, which should be fairly standard stuff as shown in the documentation and examples for OpenAL. We'll add a debug function here which lists all the available audio devices. We won't go so far as allowing the user to choose their own device out of the list, but it could be helpful for debugging in case the code compiles successfully but we don't hear anything at all. Once we have a working audio device in context, we set all the values in the arrays above to our constants, indicating no sources or buffers are set. With that done, we can also quickly implement the cleanup function. Here we just iterate over all the buffers and delete all the used ones, followed by the same thing with the sources. After that, we can destroy the context and close the audio device. Now on to the update function, which will iterate over all the audio sources and check their status to see if they are still playing. If not, we can mark the buffer for that source as unused so it can be reused later. Eventually we will also update our music player here, but let's get the sound effects working first. Okay, that looks pretty good, but in order to play any audio we first have to load it. Let's create a function which does just that, taking in an audio ID integer as well as a path to the audio file. First, we'll make sure the buffer for that audio ID isn't already in use, and in case it is, we delete the previous buffer. This code should never execute, as the game will load all the sound effects during startup, but in case you want to use this code in a different project, it's nice to have it. Now we can move on to loading the file itself. The audio files in this game are all WAV files, so let's quickly write a helper function to load those for us. The loadWave function tries to open the given file, checks its length, and then reads through the header data. We can check if the header looks valid by checking that at least it starts with the correct sequence of bytes, namely the all uppercase characters RIF. After that, we read the rest of the header, skipping through any sections we don't care about until we get to the actual values we need. To read the values, we need another helper function which will convert the buffered bytes to integers. In turn, this helper will use yet another helper, which will check the endianness of your current system. There's probably a better way to do this, and it's probably overkill for this project, but it's a fairly simple check, so there it is. Now we can finish the integer conversion function and get back to parsing the header data. We read the number of channels, the sample rate, the bit rate, as well as the size of the audio data, and ignore everything else. To finish up, we read the audio data which follows the header, and that's it for our quick and dirty WAV file loader. Now that we have all that, we can create an OpenAL audio buffer, upload the data to our new buffer, and free up the memory we previously allocated for the audio data. We'll also store the file name into our buffer names array just in case we need to debug the audio system. It's easier to look at that as opposed to just an integer ID. Now we should be able to start using our new audio system in the game. Presumably we will also need functions to actually play a sound, as well as setting values like the volume of individual sounds. Let's take a look at the header file sfx.h to get an idea of what kind of functionality we will need. Wow, there are actually quite a lot of function declarations in here, but it looks like at least half of them aren't even implemented. With that in mind, let's add functions to play a sound effect, to stop one, stop all at once, to set volume for one sound effect, set volume for all, set pan, and set pitch. Now to implement them, beginning with playing a sound. First, we'll make sure if an audio buffer with the given ID is actually loaded. Next, we will iterate over our source to buffer mapping and see if we already have a valid source for the current audio ID which is not already playing and which we can reuse. Otherwise, we'll just grab the first available source and create it if it doesn't already exist. Then we will set up the audio buffer for the given ID as the buffer for our source and store the mapping in our array. Finally, we can set up the parameters for looping, volume, pan, and pitch, and call play on our source. Next, to stop a sound, we just make sure it's loaded and call stop on the source. To stop all sounds, we can just iterate over all our sources which are in use and call stop on those. To set the volume of a sound, we have to convert the given volume to a floating point value in the range of 0 to 1, so we just divide the value by a floating point 255. Same again for setting the volume of all sound effects, except of course we loop over all valid audio sources. To set the panning, we once again have to convert the value given to something OpenAL can use, same as in the play sound function, as OpenAL takes in a parameter for position in 3D, but we just care about stereo left and right here, so we just set 0 as the values for the Y and Z axes. The game uses panning values from 0 to 30, where 15 is center, and again we have to convert that to a floating point value within the range of -1 to 1. Finally, we can implement pitch, which once again requires a similar conversion, but this time we just divide the given value by a floating point 4096 to get a value usable by OpenAL. This doesn't quite match the constants in sfx.h, but sounds correct to my ears. Now we can move on to replacing the game code to use our new audio system. Let's see what we've got there. We have a file called libsnd.cpp, which just contains empty function stubs and apparently was lovingly coded by Captain Bodger and Patchban back in March of 1995. It contains l'include and loss functions and some really fun variable names. Cool stuff. Then we also have sound.cpp, which contains the game's audio logic, and towards the end we have a few functions which have been disabled in one way or another. We'll come back to this in a bit. Last but not least, we have winsnd.cpp, which actually implements some of the functions declared in sfx.h, and this is where we'll actually start making some changes. We'll add an include to our OpenAL audio header and start commenting out all this direct sound stuff, including these fantastic defines here which look like they originated in some direct sound sample code and got changed at some point to piss flaps. Note this extern short global vol, which is the same one we used in our audio system, and we'll be talking about this variable later on. Alright, for this next chunk of variables and finisnd objects function, I'm not exactly sure if we will want to keep anything, so I'll just comment them all out for now and we'll bring them back later if we need to. All of the functions that follow and look like they have anything to do with direct sound, we are just commenting out. We'll leave the sfx_init function in, but we'll comment out the contents for now. Next we have a function called sfx_getFXBank, which is called with the path for the file wipeout.fx, which we took a quick look at in the first episode. It contains the file names of the sound effects as well as some additional parameters for each effect. We definitely want to keep this, so let's bring back the variables used in here, which we just commented out. Next we have SFX OpenFX Bank, which looks like it's actually loading the audio files into direct sound, so we'll get rid of the direct sound specific code and leave the rest. We'll add a call to our load AL audio SFX in this loop and load the sound effects and move on. Next we have some functions to sort through the array of sound effects data, which we'll leave, and then we have a function called SFX set max effects, which we are just going to comment out completely as we don't really care what the limit was back in the day. There's probably a call to this somewhere in the code which we'll have to remove later. Now we can replace the contents of SFX set volume to just call our own set AL SFX volume all, and that's that. After that we have some functions with reverb in the name, and as I recall this was used in the PlayStation version whenever you went into a tunnel. This could have been fun to implement, but sadly there are no calls to the SFX reverb on function, and there's no indication in the code for when the effect should be enabled. The next function we care about is SFX play, which we'll change to just call our own function to play a sound. Immediately after that we also have SFX play ID, which looks like the same thing but returning a value, with the original code just returning the value of whatever index in some array called looping array was null. Not sure what it should return, so we'll just return 0 for now. Next up we have a function to set the volume for a sound effect, and again we'll just comment out all the old code and just call our own function to do that. We'll do the exact same thing for the functions to set the pitch and panning for sound effects. We have a function to uninitialize sound effects, which is just calling Fini SND objects, which we already commented out, so we'll just comment out that call for now. Next we have SFX stop, which we'll change to just call our own version, and we'll do the same once again with the kill all FX function, which will just stop all the sound effects. After all this, we have a few more functions with some direct sound code, which we'll just comment out entirely. Trying to compile the project will fail because we commented out the forward declarations to sort F entries and compare, so let's bring those back and try again. Alright, now we have a missing symbol for SFX set max effects, which is also to be expected as there's a call to it in sound.cpp, which we didn't comment out yet. We have the same for Fini SND objects, which we should probably bring back in order to call our own audio cleanup function. Now the game compiles but crashes in SFX getFX bank because the start F entry variable is null. After a quick debugging, it turns out these lines in SFX init, which set the initial values for these variables, are needed, so let's bring them back in. Now the game starts, but we have no sound. Let's take a look at sound.cpp to see if we need to make any changes in there. We'll increase the value of the play channels defined from 8 to 32, as that's how much we set in our audio player, and here it's used to set the size of the channel info array, which the comment states will contain information on the channels currently being played. After that we have some functions which we won't touch, and eventually we get to init SPU sound, which contains the call to load the sound effects data. We have a loop here which will set the sound effects to either loop or not, and there are some commented out lines where extra sounds were removed from the list. We'll get back to this in a bit. Next we have update notes, where we should probably add a call to our own audio system update function. It contains some logic for when the game is paused and sound should either stop or fade out. Clearly there's a bug here as the same condition is there twice, meaning the second branch will never execute. The comment states it's the subsequent paused section, so we'll fix this condition here by checking if both the mode and paused variables are set to paused. Next we'll look at the play note function, which interestingly has a different condition to check for whether a sample is looping or just a one-shot, referred to in the comments as spot effect. This branch will set the play ID variable to -2, and that's what the update notes function is checking. This seems a bit hacky, but let's quickly check if anything changed. Still no audio in-game, so let's actually change this code a little bit. We can store the actual ID of the currently playing audio source in the play ID variable instead of the -2 here, and we'll do the same in the loop below, as well as setting the value of the playing variable to 1. Next, we'll fix the conditions in update notes to reflect these changes by checking the loop variable instead of the play ID variable. Still no sound though, so let's read through more of sound.cpp. This function called setPitch is calling some function to convert the pitch value before setting it. Let's remove the conversion, as we already do that in our audio system. Next up, the setVolume function looks fine, but it's strangely also setting the panning for that sound. This seems like a weird side effect to have, so we'll leave it for now, but also keep it in mind for later. Still no sound is played in the game, so I'm starting to suspect we forgot something. A quick check reveals that we never initialized our audio system, so that would definitely be a pretty good reason for things not working. Let's add that to our set of calls to initialize systems like the window, renderer, and input in win.cpp.
3, 2, 1, go!
Finally, we have the audio with the countdown along with a few other sound effects. It's progress, but it's also not fully working yet. We are missing sound effects from the main menu, as well as a sound which should play before the countdown called the start siren in the code. Also, you may have noticed the sound is all coming out of the left channel only, with just silence on the right. Let's get to fixing it. After a quick check, I noticed we never returned the value from SFX Play ID as we decided to just return 0. Since we changed the logic for looping variables, we should return the actual audio source ID here so it can be stored properly in the play note function. The function above called SFX Play without ID is no longer used as we always want the ID. Changing this had an interesting effect in the game audio. We now hear the siren at the start of the race, but the countdown is gone. That siren also did some fairly weird panning, and some of the game sounds are centered, but others are only in the left channel. I have a pretty good idea of how to fix it, but first let's quickly check out the code for the disabled sound effects. First, we'll bring back these commented out lines here, which set all these sounds to have their loop parameter set to 1. Once again, there's some code which appears to be setting up a reverb effect which is never used. Next up, we have some more code which has a comment saying these effects are ignored, but we want to check them out, so let's remove these. Next, we have the function adjust remote engine sound, which has an early return statement preventing it from actually doing anything. We'll comment that out and then do the same for adjust engine sound. Apparently this code which sets the volume of the engine based on the speed of the player's ship needs rebalancing. We'll make a note to do that later. Now we have adjust crowd sound, which also has an early return which we'll comment out. At the end of the function we also have a block which is disabled by an if-def, so let's define crowd sample on and see what that does. Oof, this line is only half written and below we are referring to some array which doesn't even exist. Okay, never mind this for now, let's fix the disabled sounds first. When we implemented our audio player, we used this external variable called global vol to multiply the volume of any sound effect when it's played. It seemed like a reasonable choice because first of all, its name implies that it's a global volume setting, so it should affect all of the sound effects, and also because the direct sound code in win.snd.cpp also used it in the exact same way. Let's check out how it works and where it's set. It's defined in menus.cpp without any given value, but in the same file it's also set to a value of 218 minus game data old slider pause in a few places. The name game data is a bit misleading here as it's really just a struct holding the game options data, but alright, we can live with that. The 218 implies that that's the maximum value it can ever have, as it's being set by an on-screen slider in some menu, which can also only have a maximum value of 218. Alright then, let's check where this old slider pause is used. It's found, for example, here in a commented out block of code which would have initialized the audio menu were it not commented out, so that menu option isn't available. In that code, its value is set from another game data variable called curSliderPause, so let's follow the rabbit hole even deeper to try to unravel this mystery. It looks like pretty much all usages of this variable are related to audio volume settings, so let's see where it's originally set. Here, in menus.cpp, it's set to a value of 150 in a function called initGameData, which appears to be setting up the default values for the game options. Notably, old slider pause is never set here. Alright, so to recap, we have a value of 150 set to current slider pause, which would then be copied to old slider pause if we ever open the audio menu, which we can't because it's commented out, and then the value of global vol would be set to 218 minus old slider pause. Let's just do the simple fix and set the value of global vol to 68, that's 218 minus 150, where it's declared, and call it a day. Now we have sound effects in the menu. We have the start siren, which still sounds a bit weird, and the countdown. We even have an engine sound for the ship, although it does not sound very good as there's an audible noise whenever the sample loops. Let's just quickly jump back to the set volume function in sound.cpp and remove the call to sfx effect pan, as that's not a reasonable side effect of setting the volume for a sound. Alright, nice. Now the start siren sounds better, although it's still only playing on the left side. We'll fix that later, but now a quick detour on how to improve the looping sounds. If we load up one of the looping sounds in an audio editor like Audacity and set it to loop, we can hear that the sound file was clearly not made in such a way that it will loop nicely. What we'll do here is not really rocket science. We just want the end of the sound to transition smoothly back to the beginning, so the way I do it is I pick a random spot in the middle of the file and split it in two. Then I move the first half to right after the second half and zoom in on the seam between them. I'll then select a very short range left and right of the seam such that the seam is pretty much in the middle. Then I will crossfade the beginning and the end, which will hopefully get rid of the annoying noise, and since Audacity has now joined the two parts back together, I will split them again. This time I'm looking for a zero crossing point, which is a point along the curve that crosses over the middle, and I will split it there. Now I swap the two regions again to put them back in their original order, and we're done. At this point we can export this to a WAV file with the original quality settings, which were 16-bit and 22,050 sample rate. I've done the same thing to all 6 looping sounds from the game, so that's the engine intake, the engine rumble, the engine thrust, the shield sound, the tractor beam, as well as the air turbulence. A crucial element in the Wipeout experience is the music. The original game came on a CD with the music as standard Redbook audio tracks, but since no one really uses optical media these days, we'll do something a bit different. First, let's comment out all these calls to play these looping sound effects so that eventually we can hear the music properly. Next, we can start implementing our music playback system. We'll create a couple of defines here which will let us switch between the music format. First of all, if you just want to rip the audio tracks as lossless WAV files, we'll make that possible, but we'll also create an OGG file player so we have the option of using some slightly smaller files of a reasonable quality. We'll add a function to OpenAL Audio called playALMusicTrack, which will take a track ID and try to play that music track. There's not much to say about the code that plays music in WAV format, as it's basically the same stuff as what we had earlier to play the sound effects, except this time we just use a single audio buffer and source, which are specific to the music. Now we can implement the OGG player using the Vorbis library we added earlier. Let's add another header and CPP file pair called OGGPlayer and declare two functions in the header. One which will load and start playing an OGG file, and another to update the music playback. Meanwhile, in the CPP side, we have to add the includes for OpenAL, as well as the Vorbis codec and file. Before we actually implement the two functions, we're gonna need some constants, and we'll also define a struct to hold all the data we need to play a song. Now we can implement the load OGG file function, which will simply delete any previously used audio source and buffers, and call a helper function called createStreamFromFile. The helper function will do exactly what the name implies. First, we check if the file exists and get its size in bytes. Next, we set up callbacks for the OGG Vorbis decoder, which we need to implement, starting with the read OGG callback. This callback will calculate how much data to read from the file if we're nearing the end, and then it will try to reopen the file in case the file stream doesn't exist or has errored out. Then it will read some bytes from the file into an array and copy the data into the callback destination pointer. Finally, it clears the temporary data array, and that's that. We'll just skip the close function and set it to null. Next up, we need a seek OGG callback function, which is just setting values in a variable which holds the number of bytes the song player has already consumed. This value is used by the previous callback, so it knows where to read from the file. Finally, we have a tell OGG callback function, which literally just returns the value of how many bytes have been consumed by the player so far. Now we can pass the callbacks to Vorbis by calling ov-open-callbacks, and if that succeeds, we can already read out information about the audio file we've opened with a call to ov-info. We'll read out the number of channels, the sample rate, and the duration of the song. Since we're creating these OGG files from the game music, we can just hardcode the bits per sample value to 16. Now we create an OpenAL audio source and set up all its parameters to reasonable default values. Next up are the OpenAL audio buffers, which also need to be created. We'll create 4 of them just so we definitely have enough buffers to rotate over. We could probably get away with just 2 buffers where one is playing and the other is getting audio streamed into it, but I chose to use 4 just for the sake of redundancy. Now we just fill up the buffers with audio data we get from Vorbis using ov-read, and once they are all filled, we call ALSourceQBuffers, which will queue all 4 audio buffers to be played by our audio source. Remember to free up the temporary data arrays, and we're done with this function. The update function will just call an internal helper which actually does all of the work of updating the audio stream. Here we check if we've already played through all the audio in some of the audio buffers. In case we have, we simply unqueue that buffer and once again load more audio data with OV-read into the buffer and queue it up in the source again. Back in our play AL music track function, we will set up the file path for the OGG music track and call load OGG file. If it returns a valid OpenAL audio source, we know it succeeded, so we can play the song. We should set up the music volume at this point also, but we haven't actually declared any function to do that with. Let's declare more functions specifically for music, which will serve to pause, stop, check if music is playing, and finally set the music volume. There's nothing particularly interesting here, and if you wrote the code for the sound effects, well, this is just more of that. Now we need to change the game code which previously played the CD tracks to call our own music playback functions. We'll jump into wincd.cpp and start commenting out code we don't need anymore. The cd init function is mostly useless, but it does set up some values for variables called start track and end track which we will need. We'll get back to those in a bit. Let's comment out all of CD play and include the header for our audio system. This getCurrentTrackNumber function can also be fixed to return a variable containing the current track number instead of just a value of 1. Now we can implement the CD play function, which will call our play AL music track function. It will also check if the track number to play is 1, which means it should play a random track. This won't work right now, as there is no value set for the NTOC variable, which we'll get to in a bit. Next, we can rewrite the CD paused function to ask our audio code if a track is playing. We'll also replace the code in CD resume and CD pause to call our own pause AL music track function. Next, CD stop also calls our own function to stop the music, and CD restart should work as is, except we'll get rid of this check for the do sound variable. We'll skip a few of these functions, but we'll implement CD setVol to call our own function instead. Let's try to compile the game now. It failed to compile because we forgot to link the OGG library. Now that that's fixed, the game runs, but there is no music playing. A quick debugging session shows that it's failing because it's trying to play a track with an ID of 0, which doesn't exist. This is due to the missing values which were previously set in CD init, so we'll just hardcode the correct values in there for now. We'll also add a call here to play track number 2, which is the first song, as track 1 on the CD was the data track containing the game files, just to test if the music system is working. Launching the game now starts playing the song as expected, but it stops after about a second and a half. Fair enough, we forgot to call update on our OGG player, so let's add that. It's still stopping, so let's add some breakpoints to our OGG stream update function. And now it works, for reasons I don't understand, but I don't really care enough to look into it further. The pause menu in the game lets you change the tracks, and that seems to work fine, and even the random track option seems to be working. Okay, so the CD init function was loading a file called startup.ini, which just contains the numbers 2 and 9, which are the first and last audio tracks on the original CD. That's where the values for start track and end track come from, and the value of NTOC was just end track minus 1. Now we can clean up some more of the old CD audio code. A few of these functions like num tracks, CD get TOC2, and do stuff are never even called, so they can be completely removed. Next we can make it so the game actually plays a song as soon as we hit the title screen. As I recall, it was track number 4, so we'll play that, and also make sure the music volume is set here. We'll do the same with the main menu, which should play track number 2. For some reason the code doesn't want to compile without this CD get TOC2 function, so I guess we'll just bring it back but have it do nothing. The title screen music stops after a short while, so let's add a call to update notes, which will update the sounds and music to the title screen loop. Now it works as intended, and with that we can move on from the music to other audio improvements. The original setVolume function takes in two volume parameters, one for the left channel and another for the right. It then calls two helper functions called conv-vol and conv-pan to convert those values into one volume value and one pan value. The volume conversion is just taking the average of the left and right channels. Makes sense. The pan conversion is taking the ratio of the left and right volumes and coming up with a panning value between 0 and 30, with 15 as the center. Fair enough, but it's not really optimal for our sound system. Let's change our set AL SFX volume to also take two volume parameters instead of just one. We'll do our own conversion of the volume here using floating point values, first by scaling the values to a range of 0 to 1 and then taking their average. The magic value of 16,383 comes from the original set volume function where the values are clamped to 3FFF. Now we can calculate a reasonable panning value in case the left and right channels do not have the same volume level. Luckily for us, there's a relatively simple formula which does this for us. You divide the right channel volume by the sum of the left and right channels, then subtract 0.5 and finally multiply the whole thing by 2. This yields a panning value between -1 and 1 with 0 as the center. We can now use these values with OpenAL, where the volume is just the average volume we calculated, but the panning might be slightly unintuitive as OpenAL uses a positional audio system where you can move the audio sources as well as the listener in 3 dimensions. We will not be moving the listener, so it's centered at 0 for X, Y, and Z by default, and we will set the X position of the audio to our panning value. This is not enough, however, otherwise the sound will sharply snap between the right and left channels. Additionally, we'll set the Z position of the audio to the negative square root of 1 minus the panning value squared. This results in the audio moving from left to right in a simple curve in front of the listener, and in my opinion sounds pretty good. We'll also set a few more values for OpenAL whenever we play a sound effect, namely the audio source positions should be relative to the listener and the distance roll-off factor is 0. You can look up what these do from the OpenAL documentation if you want. Now we can use our new set AL SFX volume function by passing in both of the volume values directly and skipping all the old conversion code. We'll also take a look at the play directional note and adjust directional note functions, as they should sound better now that we support a wider range of volume levels and panning. The play directional note function pretty much just duplicates all the code from adjust directional note, so we'll just change it to call play note followed by adjust directional note to set the correct volume levels. Adjust directional note seems to calculate a volume based on the distance of the given audio position and the camera position. It then calculates an angle between the camera and the given position, taking into account the camera's heading value. With those, it calculates volume levels for the left and right channels. Nice, that should work fine. We just quickly have to adjust the set volume fade function to pass the volume parameter twice, as our own function's signature has changed, and that's it for this part. The pause screen in the game allows us to change the music track, but you can only choose one of the songs or a random song. Not playing a song is not an option. We can change them pretty easily, as there's a function called getCDTrackName, which, as the function name implies, returns the name of the song corresponding to the value you pass in. If you pass in a value smaller than 0, it will return no CD, so that will work perfectly for us. Let's see here. Where's the code for when the game is paused and you press left and right to choose the song? Here it is, and it seems to loop when you go below 1 or over end track. We'll adjust this to allow for a value of 0 as well, which should do it, as the CDGetTrackName is called with a value of CDTrack-1. It works exactly as expected. Moving on. One thing which is missing in this version of the game compared to the original PlayStation version is the audio options menu. Let's bring it back by uncommenting the lines which are currently removing it. As we uncomment these defines, we also have to adjust their values so that they don't overlap with the high scores menu. Sometimes it's hard to tell what's needed for the menu to work, as this menu code is frankly just a mess, and if I were doing this as a commercial project, I would probably rewrite the whole thing. Alright, let's jump into this draw audio function and bring back the drawing of the headphones model it's supposed to show. I don't know why there's a special version of the drawing function called transform static object whole for this particular menu option, but we'll just use our standard one as always. Next up we have the code that actually contains the logic for the audio menu, which seems okay at a glance but won't draw anything except the text until we change it. We have two primitives here called slide_prim and slider_prim, which are of type FT4, which stands for flat shaded textured quad. We'll implement our own function to draw that, as it should be pretty trivial. There's nothing new here, it's just a 2D textured quad, so we do the usual conversion of values, set up our own vertices, and pass them over to our renderer. A quick test reveals there's still no audio menu showing up in the game. Looking for the word audio in the menus.cpp file reveals more commented out code, which we probably need to uncomment. Now the menu is accessible, but for some reason showing up as the high scores menu. This high scores option also needs to be incremented by 1, otherwise it overwrites the audio one. Now the menu is there, but the slider doesn't look right, and the spinning CD in the background is tiny. We'll quickly move the CD a bit upward and towards the camera. Another copy-paste fail here. We were drawing the slide prim twice, but not the slider prim. Now it looks correct, but we can also make the text blink when an option is selected. In retrospect, I'm not sure about that, but other parts of the menu also do that, so we'll leave it. The slider is picking between sound effects or music, with both at the same volume in the middle of the slider. It's an interesting choice to do it this way instead of just giving separate options for both, but whatever. This is what the game originally did, so that's good enough for me. Leaving the menu and starting a race shows that the audio volume levels work correctly, as there's no music but only sound effects as we put the slider all the way to the left. Good enough. Moving on. There are sounds in the game which are never used, specifically the remote engine sound, the player engine sounds, as well as the spectator crowd sounds. It's likely that they just didn't have enough audio channels for that on 1990s PCs, so they were removed at some point. Nonetheless, we have the sounds, and there's even code dedicated to handling those sounds, so we'll bring them back and check them out. A few of the sounds here are just mapped to another pre-existing sound, which is not going to work for us as we want to have unique values for each of them. Remote 3 is not used anywhere, so we'll just comment that out, and then we'll give the rest of these new unique values. We'll want to make sure the isPlaying function actually returns a reliable value, so we'll use the channel info data to check if that's the case, as it already contains a value for that. Now to ensure that that value is set correctly whenever a sound starts or stops, and we'll also remove these conditions that prevent the same sound from playing more than once. Toward the bottom of sound.cpp we have a function called adjustRemoteEngineSound, which first calculates the distance from the camera to the closest two enemy ships, and then figures out the volume level, panning, and even a pitch shift to simulate the Doppler effect. Looks good. Alright then, let's bring back in these functions which were originally commented out, and we'll wrap them in some defines we created earlier so we can easily switch them on and off. We'll start with the remote engine sounds, but first we need to add our own mapping for the sound files and their IDs, as we gave them all unique IDs. The mapping is simple enough. The first 30 are just directly mapped to their IDs, and then we have 31 and 32 which are mapped to the remote engine sound, 33 for the turbo sound which is actually just the missile sound, and finally 34 is the sound for crowd 2 which maps to the first crowd sound. Now we can simply adjust play AL audio SFX to use this mapping, and that should do it. Next up we go back to the code which actually plays all these sounds, and that's at the top of the general start procs function. The condition here is the same for both blocks, so we can just put it all in the same one. The crowd sounds are started in a different place. We'll come back to that. Let's see what happens if we run the game right now. It crashes due to some garbage audio ID being passed into our play function. This is happening because we don't have enough space for all the new audio IDs in the arrays set up by the game. This should be easily fixable by just increasing the value of this maxFX define here. The game now runs again, but we only have some remote engine sounds for a short bit, and then it stops. Right, so let's wrap up all these calls to the play crowd sounds, and then we'll fix the remote engine sound not looping correctly by adding these sounds to the list of looping sounds.
3, 2, 1, go!
Now we have the engine sounds from the other ships playing as expected. It fades out as the other ships get further away from the camera, and the panning seems to work fine for this effect. Even the Doppler effect is working, as the enemy ship's engine pitch is higher when it's behind you and the pitch goes down as they pass you. Nice. Let's check out the engine sounds for the player's own ship next. Okay, so the logic for this is in a function called adjust engine sound, which will set parameters for a variety of sound effects. First, the air intake sounds volume and pitch go up based on the speed of the player's ship. Next, the engine thrust sounds volume is based on the thrust of the ship, so it should go up as you press the accelerate button. The pitch for the engine thrust sound goes up with the ship thrust as well as the ship's velocity. The same treatment is applied to the remote engine sound, which is the same sound the enemy ships make. Finally, we have a section for the air turbulence sound, which has a comment saying it needs rebalancing. It looks like the volume goes up with the ship speed and will go even louder on the left or right channels when you hit either the left or the right air brake button respectively. Let's hear how all this sounds.
3, 2, 1, go!
Okay, the engine sounds pretty cool, but the air turbulence is too loud for my taste. We'll rebalance it by shifting the ship speed value by 4 bits instead of 1, which will have the effect of dividing the speed value by 16 instead of 2. That sounds better to my ears, but let's also quickly check out one of these at a time to properly hear what each layer is doing, starting with the engine rumble sound.
3, 2, 1, go!
That sounds nice and rumbly, but the sound just has a constant volume, which I'm not a fan of. Let's try setting it to behave the same as the air turbulence sound.
3, 2, 1, go!
Okay, well that's way too quiet, so let's quickly fix that and check.
3, 2, 1, go!
It's better, but I wonder what kind of effect the air brake has on it. I can't remember what the buttons for the air brakes were, so I have to check that first. It's the Z and X keys on the keyboard. Alright, let's try those.
3, 2, 1, go!
Meh, it's not really working for me, so let's get rid of the air brake calculation from the volume. The default volume for this was 8192, so let's take half of that and then add the ship speed.
3, 2, 1, go!
Okay, that's better. Let's move on to the engine air intake sound.
3, 2, 1.
That one sounds pretty cool as it is. Next up is the engine thrust sound. That one also sounds cool, so let's hear the remote engine sound.
3, 2, 1.
That's fine as well, I guess. Finally, we have the turbulence sound. That also sounds good as it is now. We'll bring back all the sounds, but I still want to tweak the engine rumble sound to be linked to the thrust value, same as the engine thrust sound.
3, 2, 1, go!
Okay, all of that together sounds pretty nice. Let's move on to the crowd sounds. For some reason, there's no declaration in the header file for the adjust crowd sound function, so we'll need to add that first. Looking through the function, it's similar to the enemy ship sound one, as it picks the two closest stadium models and calculates the volume based on the distance to those, except this one doesn't do the Doppler effect part. Let's change this part when the distance is too big to not stop the sounds, but instead just set the volume to 0. The next question is, how does this function know about where the stadiums are in each track? Aha, there's another commented out function here called initCrowdSound, which will count them for us. Let's uncomment that and take a look inside. It loops over all the landscape objects and checks their names. All the objects beginning with the word lost are the stadiums, and in fact the full name of those objects is LowStad, presumably because they're a low poly model of a stadium. When running the game, there's no crowd noise, even though we start off right next to some stadiums. Let's debug this real quick. Great. The init crowd sound function has an early return 0, which is definitely not what we want, so let's comment that out and try again. Now it returns 10 stadiums found, and we can hear the crowd noise in the game.
3, 2, 1, go!
It's panning very harshly from left to right though, so let's see if we can quickly fix that also. Okay, everything else looks good, but we actually need to increase the value of max FX by 1 more so the arrays also fit the second crowd sound.
3, 2, 1, go!
And that seems to work well. The panning is smooth, and whenever we go past the stadium, we hear the crowd cheering. I think that just about covers it for the audio in the game, so we'll call it a day here. In the next episode, we'll add the missing HUD elements and do a whole bunch of cool improvements to the game, including ambient lighting, as well as higher frame rates, so stay tuned for that. Thank you for spending your time with me, and I hope you've enjoyed the series so far. See you on the next one. Later!